Hello, this is Camille, and in this video I'm going to show you the functions RayLab has for modeling beam splitters. So let's jump right in and add a beam splitter to our model. RayLab currently has two different types of beam splitters, the cube beam splitter or the thin or pellicle style beam splitter. So for this demonstration I'm just going to select the cube beam splitter, and the first thing that I notice is that the rays are actually not being split by the splitter. And that is because if you go to the system options, you'll see that there are three different ray splitting modes in RayLab. In the first mode, which is disabled, the rays are either reflected or transmitted depending on the reflectance of your surface. So if I set the reflectance to anything less than 0.5, all of my rays are transmitted, and for anything greater than 0.5, they are reflected. So let's go back to system options and try the different mode here, which is to split the rays at splitters. In this case, the rays are split at any beam splitter surface. And if I go ahead and change the option down here for the ray intensity to brightness, you can see that I even can tell the relative intensities between the reflected and transmitted rays. Now I should point out that this relative brightness is non-linear as compared to the actual intensity of the ray, and that is just to enable us to better visualize really faint rays. So in this mode, if you change the reflectance of the beam splitter, you can see how the transmitted and reflected rays change. The other option is to show the ray intensity as width, and this just provides a different way of visualizing the relative intensities of your transmitted and reflected rays. Now there's also a third ray splitting mode, which is this with Fresnel equations case. In this case, the rays split the same way as before at splitter surfaces, but they also split at ordinary glass surfaces according to the Fresnel equations. And there's a link to the Fresnel equations in the descriptions below. So to see this a little more clearly, let's reduce the number of rays that we have to 1. And let's change the angle slightly. So you can now see that the ray is splitting at each glass surface, and there is a reflected portion and a transmitted portion with relative intensities that are calculated according to Fresnel equations. And the transmitted and reflected intensities at the splitter surface are still based on the specified reflectances of the surface. Finally, if I look at the beam splitter options, you'll see that so far everything that we have described has had to do with the non-polarizing beam splitters, but RayLab can also model polarizing beam splitters. In that case, there are different parameters for the reflectivity of the S and the P polarized rays, and this of course can be used in conjunction with the polarization ray tracing capabilities of RayLab, which will be described in another video. A great example of a beam splitter is shown in the Michelson interferometer sample which ships with RayLab. This model consists of a beam splitter 50-50 and 2 mirrors which return the split beams back to the splitter and direct them to combine onto an image surface. You can actually look for the interference patterns on the image surface by using the coherent detector option of the analysis window. And in order to get these fringe patterns, I have actually tilted one of the mirrors in this interferometer slightly relative to the normal.